Okay, thanks for having me, Tony and Warren, and for logistics, Lori and Eve and company. Thank you so much for having me. It's great to be here today. Before I start talking about machine learning, a little bit of history is always good to set the stage of where I'm coming from and why I'm discussing the topics that I'm discussing. So 4 years ago, I was at University of Pennsylvania as a bioinformatics researcher, doing project-based support, running HPC infrastructure, and by that point, you know, the genomics as a wave of technology was already well on its way to transforming many areas of life sciences and biology, not only with respect to the types of questions you can ask and answer with this new technology, but also transforming the field to be more data-centric, more computer science-centric, and really changing the tool sets that researchers needed to use for their own analysis. It's simply transformative. And in a parallel way, cloud computing was just using the same sort of full wave transformation for IT and infrastructure and high performance computing. Suddenly, everybody who had a credit card had access to a top 500 supercomputer, which was not the case, you know, several years prior to that. What we're seeing today with machine learning is a similar large wave transformation of the way people are using technology to inform ourselves, our research, and really get at problems that were intractable prior to this new technology coming in and transforming ourselves and our research and our industries. So machine learning on the cloud, that's what we're going to be talking about today. I think my computer is frozen. That's always good. All right. Sorry for the technical difficulties. All right, here we go. It might go really quickly. Here we go. All right, so what is artificial intelligence? We'll discuss that a little bit more to make sure that we're all on the same page. What are the challenges with artificial intelligence? Generally, why it's a hard problem and what we think we can do about it. Specifically, we'll dive into Apache MXNet, what it is, and how it applies to machine learning and artificial intelligence. And time permitting, if we have time, because there's a lot of material to cover, we'll do a live demo, you know, fingers crossed. So artificial intelligence. What we mean by it is essentially a system or services which can perform tasks on behalf of humans. Now, this isn't really replacing human intelligence. We really think of it as assistive technologies, but essentially they were problems and services that were not able to be done prior to the invention of artificial intelligence, other than by humans, maybe a smart monkey, but still a physical animal trying to do a task. We think that these technologies are fantastic in lots of different ways, but the tool to make these types of services and systems a reality is really all based on research and science that was developed and started to be developed even before computers were a thing, and that's machine learning, right? So there's two general classes of machine learning. There's either supervised, where you're learning from labeled data. That means that there is a source of truth out there. There is a data source, and there is some expert that has gone and validated and said that this source of information is what we think it is, to our best knowledge, right? And you take that labeled data, you train up a model, you figure out what are the features of that data that are intrinsic to the particular quality that you're looking for, and then use it as a basis for classification of new data that's coming in of similar quality. There's also unsupervised learning, where essentially you're taking a naive approach and finding out what are the features of that data that are intrinsic to make groups, categorizations of groups and clusters of groups available as categories that you can go back and say, okay, well, we know these things are related in some fashion. They are a particular strain of bacteria, you know, a given disease condition, locality, and so forth, and basically be able to then reapply labels that we know of for these particular groups once we see the commonalities across them. So machine learning classification has fairly understood core components. They're at the most basic core. It's a measure of similarity against two things, whether that's a Euclidean distance or a vector of values and how they relate to each other to try to find trends within the system. And here, a plot on my right, your left, is a Pearson correlation between holes in your house and how many mice you expect to find in it. I think there's a pretty causal relationship. You know, caveat emptor, correlation doesn't always cause causation, but I think you can figure out the mechanism that the mouse gets in your house if there are more holes in it. You take those basic kernels of operation and you start building upon them more complex systems, whether these are hierarchical clusters, so you have two things that are related to each other. What else is nearby in this relationship? Does it form a cohesive whole? And what is the cutoff or distances that you could think of by these hierarchical clustering groups to make them the most similar sorts of groups? So you have some variability within your groups. They're not all completely homogeneous to each other. They're not complete clones, but they certainly are related in some fashion in a way that makes sense for the biology. And you can either do this as pairwise iterative clustering, or you can use naive random centroid dropping within the groups and then doing iterative reassignment of where that centroid is until you come to convergence, as K-means clustering does. And finally, once you have labels, once you have these groups, you can start doing higher order processes on top of these categorizations. So this is about the mid-'80s that finally folks started using these categorizations into decision-making frameworks, right? So given that you know somebody who's age 40, they already own a house, they don't have much credit to them, yet they have a relatively high stable income, it's probably in your best interest to extend them a line of credit as a bank because you know they have stable resources and they're a low-risk investment. But even still, these are powerful models that are well used within a lot of business systems, within a lot of healthcare to decide treatment for folks. But the things that you can do with these simple categorization and decision matrices is not that hard. It's not that complex. It's still within the bounds of what you can do using intuition, in my opinion, right? All it does is it takes our intuition, codifies it into a simple model, and then automates the process of making a decision in one way or another. Today, we have these things called deep learning models. They're in the class of machine learning algorithms, and they take the models that we've known in neural networks and apply many layers of nonlinear processing to input data that's coming in. Let's see if this laser works right. So you have input data that's coming in, whether it's still images and lots of still images, or whether this is video, or whether this is sound, so sigmoid data, metabolic profiles, binary data, whether, you know, yes or no, like such as chromosome assignment and gender, birth gender, or text information coming in, such as doctor notes, and then you put it through these neural network models to extract the features and apply weights to those features to transform the data in some way. That output gets fed into other input models and nodes that are extracting additional features on that data and so on and so forth, till you come out with a final prediction based off of new data, right? So new data comes in and you say, are you able to categorize it? You do an extremely bad job, and that's where the model fit portion of this comes in, where you're feeding back the results of testing, what your predictions are, back into the model to feed it forward again, so that you adjust the weight matrices of the features for extraction in each layer, so that when you get to the activation phase, right, so you have a set of features, does that feature need to meet the criteria for significance of information, yes or no, or on some range, it gets forward in the right way so that each successive layer of these models become more and more accurate as you adjust the probabilities that these features are significant for the type of answer that you're looking for. right? And the outputs are anything from image segmentation to say things that look like bicycles versus things that look like people, or faces across time and how they related, or other things like you can do wholesale transformations that combine different types of data, right? So you have an image of people riding bicycles. You can apply a label that's really quite accurate that says people and bikes are in this picture, but not only that, you can take our knowledge of how English is structured and give it a human-readable title, people riding bikes, right? Which seems simple and intuitive, but is a lot harder in practice than you would think. My favorite example of taking sort of two disparate sources of data for training and styles and transforming something into something else is sort of deep learning art. If you go to deepart.io, you'll see some really applications and other stuff that are starting to apply stylistic, learn stylistic reinterpretations of images to be famous in the style of famous artists. Someone took those models and said, I'm going to feed as a style a very old-timey floral arrangement and then give it pictures of dinosaurs. So you have these really cool pictures of dinosaurs made out of fruit or flowers. It was really pretty fantastic application. So we want to get to the point where people do cool stuff like this that you never have thought of for medicine, right? To bring it back. So what are some deep learning applications that we've seen out in the field? We've seen folks applying this image processing technology for predictive pre-diabetic conditions. Are you pre-diabetic? Can you notice it early on if you take high-resolution images of your retina? They came pretty close. They're not as good as manual review of retinal images, but certainly a lot cheaper and almost as accurate. So at the very least, you could use it as a screening technology to flag folks who should go into a manual process as opposed to reviewing everybody, right? We saw recent work just a few months ago taking the same approach for melanoma and carcinoma from mold. This work is another deep learning model. These red dots here are expert level categorizations. All of these lesions were biopsied, so we know two. And you can see the significance curve is actually, the algorithm is actually quite good and sometimes better than the manual annotation, sometimes worse. Here in the case of melanoma or right on it. But this is really promising. That not only is it categorizing whether this is something that you should biopsy, but also what is the likely category of that this biopsy is going to come out at. So that's really promising work. And that's really only taking one type of data, one model through this fairly complex deep learning chain. We also have companies doing full PHI and taking different types of imaging technologies, whether these are PET scans, MRIs, and blood flow, and combining them into very complex models that are going to inform our diagnostic capabilities in automated ways. And that's an extremely powerful model. So it's not just medicine where other industries are being transformed, especially autonomous driving systems, where you look at optical. This is one of the most accurate autonomous driving systems. This is driving in Beijing. You can see that there's very good categorizations of what the cars are, and the labels here. I can't read Chinese, but I assume it's the license plate who it belongs to and saying what it is. But it's fairly easy to do this when you've got great images in daylight, right? It's much harder to do this at night where you have high field, beams coming at you. I know I can't really drive at night all that well. I can imagine what a computer sees. But you still see that it's really, it's getting all of the cars and identifying them in extremely accurate modes, even in low light conditions. This all happens in real time. Right here is per pixel segmentation of the road surface. So it's really important to know where a road is and where a road isn't if you're a car. Right? And not only that, you can actually take all of this over time and build a model that not only does the per pixel road image segmentation, tell you where you are, it can also give you centimeter accurate positioning just using optical techniques. This is not using LiDAR at all. Right? But cars are fairly big. You can fit a big computer in there, right? You can imagine that the computing power needed to do this, this at-the-edge compute and sub-millisecond decision-making, cars are actually a fairly friendly environment. What about other environments that are smaller, whether these are biological sensors that are spread across a building or out in the field, in a farm field where you're resource constrained? What happens there, right? So here's a movie of a drone where we took a model that was trained on finding a person, and this small drone is actually following this person in real time, right? So it's fairly unbalanced because it was tacked on the top of a drone that wasn't meant to hold this very small card computer. But you can see that even in small power-constrained environments, you can actually do fairly sophisticated things. So we think that, essentially this image technology, deep learning models that you're training can be applied to the field, do really transformative things, and are excited to see what the community is doing. But it's not all images, it's not all video. There's also a huge potential for voice systems that we're actively looking at. And I'll talk a little bit about our voice service and natural language processing and understanding service, that can probably a little bit later. But there's a lot of, we've had a lot of outreach from various of our customers spread across the private, public, and research ecosystem, looking at applications of voice technologies, new applications of voice technologies within healthcare. So that's a pretty exciting field. If you're interested in seeing a video, you can go to our YouTube channel and search for American Heart Association and Amazon Lex, and you'll see a video of how they applied our chatbot technology and our voice technology for looking at healthy outcomes, healthier cardiovascular outcomes and lifestyle things. So that's pretty cool. So now that we have a broad sense of what artificial intelligence is, what machine learning tools are applied to artificial intelligence, the types of problems that people are tackling today, let's look at the challenges. Why is this a hard problem? Well, I think you can make a party game out of somebody who works for a cloud company and talks about scale. Every time I take scale, eat a muffin or something. But but this really is a problem for artificial intelligence and building models. And the first scale problem that you'll reach into is data, right? If you don't have the right data to train your models, you're not going to get anywhere. And we've seen from real-world evidence that some of these models really take terabytes, petabytes of data to train. We've even seen some models that take exabytes of data to train. Our good friends at Mountain View just recently published a paper where they're still seeing linear improvement in their deep learning models as they give it tons and tons of data. Some of the biggest data that's out there, they're still seeing linear improvement with log-scale data. So keep feeding data to the beast, it'll keep getting more and more accurate over time, which is really pretty amazing. And traditionally, the scale of data used to be dictated by your resources, whether that was a single computer up to a data center, right? Walls dictated the problem that you can solve, which is absolutely bonkers. So you really should think about, okay, what is the problem that we need to solve, get the data to that problem, and start training these models, which it's obvious when you think about it, but honestly, people don't think about it at all. They're ingrained to think about what are my resources, therefore what are the questions I can ask, and therefore what are the actions I can take within my research. And I think that we have a pretty strong value proposition for not being constrained by your resources, at least for when it comes to data. The other thing is training, right? Training these models, especially in the case of deep learning, takes thousands of hours. We've seen models that take weeks to train effectively on that big, humongous piece of data to become an effective model that you can then translate out to the edge. So don't underestimate the compute requirements needed to even act on data training. It takes tons of compute power. GPUs are super expensive, not only to procure, but also to operate. Their per core wattage hours are incredibly high and really add to the ongoing costs of machine learning. And finally, there's prediction. once you actually have a trained model, once you have data coming in, being able to act on new data as it comes in real time is actually a hard problem, right? Especially when you're looking at sort of time-based. Okay, so take population health. You have an outbreak. How fast can you react to it? How much data can you come in from your centers and be able to apply decisions in real time? How do you deploy predictive algorithms out to the field is a problem, and it needs to be solved. So at least for AWS, existing data, actually new data is actually the easiest thing. We actually, people just have cloud-native applications being sent into AWS all the time. We're aggregating quite a bit of data as it goes. But for the existing data, right, so imagine you're a satellite company who has, 100 petabytes of historical data over time, and you want to do climate research on that. How would you get that 100 petabytes over the wire into AWS? They say, don't do that. Use a truck. We have a semi-truck that you can get into your data center, copy the data over in about a week, an exabyte of data, and then send that thing off to our data center for copying in a couple weeks too, right? So in less than a month, you can get up to exabytes of data into AWS fairly fast. And, as I said, we have folks just sending in data into AWS for training in whole regions. For training, we have tons of GPUs. We have over 1 million customers daily, active customers daily. And in order to meet that demand across a lot of different industries, we have a broad set of resources. And specifically, you as researchers should take advantage of the fact that we have a lot of other customers training deep learning models on AWS, and they train, and then they have to let go of those resources. You should take advantage of that and be able to take on those resources when you need it, and then drop them when you don't and stop paying, right? So that elastic capacity of cloud services is really critical for cost-effective training across tons of data. And also we have tools and services like pre-built deep learning images that I think are easy to take up. Not only that, not only are pre-built images, but there's whole communities out there that are starting to develop reproducible science by publishing images along with their publication, along with the specification of how to run those tools on the input data to get the exact output for that publication. So I think that's an incredible model for reproducible science, and again, another thing that is enabled by having these mega-scale architectures available to anybody who can come up and have a modest means to perform an experiment. And finally, for prediction, those tons of GPUs come back in, but we also have CPUs, so we can deploy the learned models. You might not need as powerful as a Tesla K80 GPU for applying the prediction. You might only need a graphics-capable GPU that has less double floating point position, right? So applying the models, we have those sorts of different types of resources as well. We have serverless technologies, so be able to scale and deploy on demand and only pay by the 100 milliseconds. And then at the edge, we just released services for the same types of things that you could deploy in the cloud out at the edge, either in IoT devices or within compute cores that are very close to IoT devices. So what about Amazon? Amazon AI, right? It's not an unfair statement to say that Amazon's one of the biggest machine learning. Amazon Retail is one of the biggest machine learning success stories that we've seen, right? Being able to even say that folks who buy diapers might also want baby wipes is quite a thing that caused our success. So we took the lessons learned. So this is Alexa, right? Here's a device that you speak to, ask questions, and interact with to control your home. We took the underlying technology of this specific device and created services like Amazon Lex and Polly. So this is a speech, natural language speech engine, and this is a natural language processing and understanding service, and a image recognition service. So you can we have pre-built models that you can send your photos to, and it will be able to look at and identify faces whether you're smiling, the approximate age of the person, and other things. And we've seen some interesting uses, which I won't get into today, using the recognition service to do automated processing of persons of interest for police departments. Again, if you're interested, look up Amazon Recognition on our YouTube channel. There's quite a few sessions on how it's being applied out in the field. In addition to these sort of pre-built models and pre-built services that folks can take on is an AI platform, right? So we have a machine learning service that applies, clustering and support vector machine simple models, not a deep learning service, mind you. These are the easier things to pick up and use, and quite frankly are good for the majority of things that you want to do within machine learning. But when the machine learning managed service doesn't really apply for the use case, you also have the underlying platforms like Elastic MapReduce, which provides you easy access to Spark and the Hadoop ecosystem, as well as other services coming in 2017 that will help you to be able to do more advanced model building and training within the AWS platform. For AI engines, today we're really going to be focusing on Apache MXNet, but I don't think I think it's also another true statement that we probably have more TensorFlow workflows happening on AWS than any other place on the planet. So we support TensorFlow, Caffe, Torch, Piano, Keras, Microsoft CMTK. All of these frameworks work extremely well on top of AWS because we are a generalized infrastructure provider, and we also provide a managed AMI, which I'll talk to you later, that has all of these things pre-configured and you're ready to go. And finally, we have infrastructure services. So what we built our business on was rock solid and scalable on-demand compute, whether this is FPGA instances, P2 instances, which I'll cover in a bit, services like Elastic MapReduce or Batch for batch computing, or serverless services like Amazon Lambda or AWS Greengrass, which is the aforementioned, deploy serverless technologies at the edge. So for P2 instances, right, I did mention that we have tons of GPUs. This is the underpinning of our platform for training. These are EC2 instances that have 8 K80, Tesla NVIDIA K80 accelerators. That means you have up to 16 separate GPUs, all on a very high bandwidth, 10 gigabit per second PCI bus, so you're able to interconnect all of the memory across these GPUs and all these cores. Has quite a bit of memory within the biggest instance, so 732. So 32 physical cores, 64 hyper-threaded Intel cores, and you can't see it here, but it's up to 20 gigabit placement groups, so these things can connect over a 20 gig point-to-point transfer protocol. So these are quite powerful machines. You can do some big compute on them. And we also just recently announced our next generation of P3 instances that are going to come with NVIDIA Voltage, right? So these are what NVIDIA announced during their AI conference recently. These are machine learning beasts. This is what I mean. So these are the K80s that we have today. You can do this long short-term memory training model. This is standard set in about 36 hours. The P100s, which is their current card that's out in the market today, will reduce that to about 20. The Voltas will get it down to about 8 hours, training the same model. So it's a really fantastic machine. It also has tensor cores and a bunch of other stuff. But the gist for today is that MXNet is already optimized for Volta. So the models that you're seeing today on our P2 instances and other NVIDIA hardware will translate directly to what MXNet is able to do with minimal to no code changes. So that's pretty powerful, right? So I mentioned our supported frameworks. The way we do it is in AMI, which stands for Amazon Machine Image. Basically, this is a box which I've bootstrapped already, but I'll show you how to do it later on if you have demo time, where you have up to 40,000 cores if you use the P2 16 extra large, or you can use it on just CPU-only boxes. It has pre-configured Apache MXNet, Python, notebooks, other tools, everything that you need in order to start machine learning. This is a managed compute instance that you can rely on. Great. Let's see where we're at. Ooh, 35 minutes. I better start going. So, overview. Why did we pick MXNet or or why are we putting an emphasis as a company on MXNet? First is that it's programmable, right? It does have a C++ core, but one of the tenets of Apache MXNet was to provide connectors to a lot of different programming languages, whether that's JavaScript, Java, anything that runs on the JVM has a fantastic hook into MXNet, but so does Python and Julia and other languages. So it's got multiple ways, and R as well. It's got support for multiple languages, and it's really simple syntax to build your models. It has a lot of pre-configured tools. The models that you do build are portable outside of that, so it's a very highly efficient with respect to memory, about half as much for a trained model as other frameworks. So you can deploy this model into really tight architectures where you're resource constrained. It also has near linear scaling across hundreds of GPUs, not the cores, but physical GPUs, and I'll show a bit of that later. It's part of the Apache Foundation. We're doing a ton of development against it and giving that back out to the community, because we feel like leveraging the support of the community is the best way to make progress on this really important problem. So at Amazon, there's a host of things that we do, right? I did mention the diapers, but we also, robotics. Being able to position a rack of bins in 2 seconds faster is actually a big deal, right? So robotics are huge. Computer vision and other models that control our retail business, but also our cloud business, so scheduling. Having 1 million customers all asking for machines at the same time, we should be able to predict what our demand is and how to schedule that before we even get those requests. I mean, that is a machine learning problem. So we use MXNet across the company, all companies. Here is a graph of the efficiency. The red line is ideal. The blue line is the actual. And across a single box, you see close to 91% efficiency for scale-up adding GPUs, which is really pretty fantastic. But not only that, if you go across GPUs, so here's up to 256 GPUs, you have an 88% efficiency. So that's pretty fantastic. How does this, you might be asking now, well, that's great. How does it compare to other frameworks like TensorFlow or CNTK? Basically, we think, again, the owner should be the community, not a for-profit company. We have imperative and declarative syntax. I'll get into what that means in a bit. It has a lot more, as I mentioned, language support, and also the complexity of developing is lowered as compared to other frameworks, right? So 107 versus 44 lines of code. I don't know if you've ever been a developer, but I quickly lost track of what I was developing if it wasn't short and sweet, right? So brevity is the key here. But not only that, again, I mentioned before, the models that you train and give out is much smaller than other frameworks, which means that you can put these things on resource-constrained edge locations. All right. So what are the basics? So the basics are you've got data structures like array. If you're familiar with programming in Python with pandas or NumPy, ND array should be a really fairly intuitive concept for you. There's also symbolic expressions for neural networks, right? So we have these symbols that go into our declarative programming, modules for intermediate level and high level interfaces. So there are modules, for instance, for a convolutional neural network or other types of learning models that you can just pick off the shelf. You can think of those as the equivalent of like an R package, right? A lemma package where you can take a big thing and just really apply it to your data frame. That's how you could think of modules. And there's also a lot of functionality for loading in data from different types of places, and it has a mixed programming model. Not listed here, it's also natively data parallel, which is how it achieves that close to linear that close to linear performance even at hundreds of GPUs is because it distributes the data as a core functionality and works on the data as well. So feeding the beast of a GPU, especially when you have 2,500 cores, is not an easy problem. Let the framework do it for you. All right, so here's an example of iterative programming. If you've ever programmed in Python, it's basically, you know, it's really simple model. Everything happens at the point that you write it, right? It gets, so for here, the variable A is already populated by 10.1, right? So at the point of definition, there is execution. For an imperative programming is really, you know, so what are the advantages here? You have easy to tweak in Python. You know, you already have a very familiar model. It has a lot of frameworks which you can use. The cons of this style of programming essentially boils down to performance. It's really hard to optimize when you don't know what the next line of code is going to do. For a compiler, these scripting languages are fantastic for development, but they're not so great for ad hoc optimization. So the declarative model here is a little bit different in that you're declaring what something should look like, and at the end of all of this iterations, once you get into the imperative style programming, then you decide what the optimizations are. So right here, the pros are that you have more chances for optimization, right? Because here in this fourth line down, where you have D being defined by C and 1, you can say that, well, this actually can share memory space since we know later on we're about to delete C and not use it. So we can use the same address space for this given computation. A lot of, because of these optimizations that you can apply at runtime to a compile, loop, and rolling and other things, a lot of frameworks, TensorFlow, Theano, Caffe, all use this declarative style of programming. The cons is it's a little bit less flexible, but in terms of MXNet, you can actually do both. Here's an example of doing imperative programming, and here's an example of declarative programming where you're defining what the deep learning model looks like. Here you have a variable of data being defined, and then you have a fully connected node with a label output, and then this module. This is our actual model. And then you feed it your data to assign back into this variable of data, right? So you've built the model, you've declared what it looks like, and then you give it the data at the end to crunch on. Right. I think this is sort of covering the same thing, so I'm just gonna skip over it in the interest of time. So once you have your models, once you train them, it's really easy to compile for any platform and then stick it in there. Here's an example of integrating it within an Android phone. If you could hear what's being said, this video is going through and scanning what it is and saying, I found an apple, I found a banana, yada, yada. For here, it's embedded within JavaScript engine itself, so this requires a browser extension, but you can run in the browser to go right ahead and do those labels of a puppy. And who doesn't love labeled puppies? All right, so what is the roadmap? Where is MXNet going? Where would we like to see it go? First, sort of the areas of interest of MXNet really have to do with usability, make it more usable, make it friendlier with better documentation, and put it within other frameworks. We want to support all major platforms and even some smaller ones. Keep iterating on the language bindings so that they get better, and then really start going back and looking at the sparse data layers, right? So especially for healthcare and genomic data, these are going to be extremely sparse representations across a population. And to get at the value of that data, we're going to need representations that are memory efficient. So that's something that we're very interested in, as well as training performance improvements. Amazon itself is working on better ways of deploying these models. We think that that's really important, the ease of use, to really democratize machine learning in the same way that we've democratized, for instance, standing up a website, which used to be a hard problem. We think that being able to easily deploy what you built into different environments is the key to broad adoption. So, developer tools and resources. What do you have available to you? I discussed the deep learning AMI. Again, it has all of this stuff pre-configured. Not only does it have this one, this big hunting machine with all of these things in it, we also provide a template so that you can launch a pre-configured and pre-connected cluster of these resources so you can tackle large problems. So you can develop in a single instance, and then when you're ready to go on your big data set, go ahead and launch that template. You've got a cluster that you can crunch on, and then drop it off so that you stop paying and you do this efficiently. All right. We also have Docker container images on the way, right? So that you can deploy these things within other types of environments and services that require Docker and other container technology. We have a host of notebooks. Again, I think I'll have some time for the demo, quick demo. But this URL right here has a bunch of notebooks that go through the basic concepts of MXNet, such as MD arrays or symbols. But it also has some examples, and this is the demo that I'll hopefully get to, where you got recognizing handwritten digits and other sorts of problems. You've got developer resources here. All right, so let's take a look at this demo. All right, so I'm going to keep out of that. And my computer's frozen again. While this is going, are there any questions? Where's my mouse? Is my mouse going? Oh, there it is. Okay, so let me go this way. No. Perfect. Make this bigger. That should do it. Take this URL here, stick it into my handy dandy browser window. Starting up, starting up. Live demo, please. I don't recommend them. All right, again, this will start up in a second, and when you start seeing some stuff go by. Yeah. Sure. I'll repeat the question. Yeah. Okay. That's better to have the microphone. Yeah.
You mentioned a lot about the compute power on the cloud, but what we see mostly is that getting the data there, what will take most of the time and the money. How do we work around that?
So I'd push back a little bit on the money piece. Obviously, time is money. So but there's a couple ways, right? So we have fairly large bandwidth to research networks like Internet 2, ESNet, and other things around the globe. So I challenge folks to think about using over the Internet transfers into S3 and test it out and see if it actually works for you. you should be pleasantly surprised. The key to moving data anywhere has to do with parallelism and parallel streams, right? So anytime you have a single point of transfer, you're going to get bottlenecks. If you look at science DMZs, for instance, they're really keen for that. The reason they became a thing was because of institutional firewalls acting as a single point of bottlenecking between institutions. And the way they got over that is to do a parallel path. So they're still doing sort of not that many threads of parallel copies out. I have been guilty of taking down our firewall, so I know, right? So and if that's the case, really there's the SneakerNet option, right? So we have a box that you can order that has 100 terabytes of space. You bring it into your data center and connect it up to ISO or 10 gig E. Put your data on it locally and then send it back. Right, that's okay. Sure, but if you're not able to do the problem in the first place, how much time is that, right?
The utility of the cloud versus like whenever we get compute that's local. So you always just like have to add the price of you're moving to the cloud, and you have some compute local here. So overall, how do you make a decision that do I take this problem to the cloud or
right? So you know this comes up a lot. Like, how do you balance the fact that you have on-premise infrastructure investment? We say, good, use them. We're not an all-or-nothing organization. We actually recommend on a regular basis of how to best utilize your on-premise infrastructure. And if that's the solution, we'll be very upfront to say, yeah, this should work for you. You really don't need AWS. We're incentivized to say that because we honestly put you first. So in that vein, though, there is a hidden cost to it, too. A lot of times, on-premise infrastructures are shared across groups, and you actually can't get access to the entire thing. So if you've got an idea, again, you're resource constraining yourself to the problem you can solve today. I think it's very easy to calculate what the cost is for any given experimental question, especially when you have upfront pricing, and you do that cost calculation. Okay, if we can do this experiment for a reasonable cost and it will be over in a week, why don't we? Right? Because it's there, and then you take the data down, and you have a set cost. That's exactly how researchers should be thinking of burstable compute models. So leverage what you can based on the budget that you have available. Moving data is always going to be a problem, right? So think about, let's talk about TCGA, right? It's close to a petabyte these days. That means you're paying to have TCGA, which is public data, on your on-premise infrastructure. That's about $1 million a year, right? That's not an unreasonable thing to have on on-premise supercomputers that are shared across an institution. Yet, it is a sunk cost. So you should always think about that as well. What is the reference data that you need for your experiment?
Yes. Really good presentation. Just curious, we do a lot of genomic computation analysis, specifically on the cancer genome arena. And I asked one of my team members actually to look into the possibility of using the GPU, close to an AI type of analysis. But we do have an HPC system here that is called BioWolf. And the concern has always been that converting the algorithms that we're carrying out some of the analysis is really complicated for some of these GPU resources. Has there been any movement in that regard, trying to make some of these genomic algorithms available so that way I have no doubt that it's faster, it's potentially better in terms of the efficiency, but there are very few algorithms available there that you can actually use using the GPU versus the CPU.
Yeah, I completely agree. And it boils down to feeding the beast, right? Being able to pump as much data in a parallel way into that GPU architecture. That's always been the problem with GPUs, especially in bioinformatics. There has been some work by Intel to increase the efficiency of the single instruction, multiple data type of architectures, which is really what AVX registers are on Intel chips, and what the equivalent is for a GPU is that you're sending, one type of transformation, lots of data to it. They've been working on that and have developed back into at least DWA-MEM and haplotype caller. And now that GK4 is fully open source, a lot more people are going to have access to that, to those implementations that Intel has done. There's been other work in it. So I'll raise up one of our leading partners for FPGA instances is Edico Genomics, right? So Edico Genomics, Edico Genome, sorry, developed an FPGA algorithm for doing whole genome analysis on FPGAs. They're able to do a 30x whole genome in about 20 minutes, which is, really fast. So it's still specialized. I think as having access to the hardware is the first step to transforming the algorithm. And now that you don't have to have a capital purchase investment in very large GPU clusters, we're starting to see frameworks that come out to be able to utilize them easily, like TensorFlow, like MXNet. And that is what will feed into the future. So I think that we're getting there to where you want to be. It's still early days. I think I may or may not be able to do this demo. It might be blocking.
Yeah, I have a feeling we'll have a problem there. I just want to say if there's anybody online who has a question, you can just raise your hand and we'll open your mic on that. Is there anybody currently online? Okay, another question here in the room then.
Well, this did work yesterday, so. But if you're interested, I literally just followed the instructions here for starting the Jupyter notebook. It is this notebook that I was going to show. I did not follow the instructions for installing anything because all of it is installed in the Deep Learning AMI, so you can just get started right away.
Yeah, I think you mentioned earlier, one of the slides you compared MXNet with the TensorFlow, but definitely MXNet have the computational advantages in terms of programming or the model size. But can you comment on this in terms of precision accuracy? There's actually any difference between all these different algorithms? There's many available. Deep learning algorithms are available. Open source is available. So.
Yeah. Actually, it's so dependent on how you apply the problem and how you do your feature selection that's an impossible question to answer. I think that the math should still be the same intuitively, so you should get the same answer, but random bits and random seeds are always the bane of our existence in informatics. So the nice thing is that you can try both right in the same platform, right? Like I said, TensorFlow works fantastic on the P2 instances. MXNet works fantastic. If it's a very similar programming model, go ahead and try both. It's worth your while, especially within research, to increase that could translate back into human health, to use the tools that are available to you. So if you know TensorFlow already, go ahead. Why switch to MXNet, right? I think that the community and the individual researcher should decide that. That's not something that we're going to put our foot down. We just like MXNet.
We have a couple questions on the phone. Denise, go ahead.
Yes, thank you. Very interesting presentation. Thank you very much. I have a question about what we anticipate to be the scenario where we have a lot of data files that are sort of arbitrary formats created by individual researchers going into a data warehouse. And so when you talked about the kinds of data that this is successful with, you mentioned imaging, video, speech, events, and text. Is it equally effective if you have a data warehouse where all the data has been harmonized from these different heterogeneous files into one common warehouse. But it's more, like clinical data and not of the type you just mentioned, structured clinical data. Do these techniques?
I think so. So imagine taking your data that you've transformed into an I2B2 data warehouse, right, and feeding it into these natural language processing models. I think you could recreate Zach's finding about Vioxx and cardiac events fairly easily using structured data like this, right? And not even a deep learning model, probably a SVM would be enough. So clean data is so much easier to work with than messy data. So I think it'll work better, right? Because you've already done the hard work of homogenizing the data. You can actually use the signals are clearer within that data itself. The reason deep learning models were being applied in this field and they're having such success is because they overcome the noise factor from randomness, even mislabeled data, as you add in more data, and it's able to identify things that aren't real signals.
Great. We had a second question on the phone. Gaurav?
Hey, great, Angel. This is Gaurav from Seven Bridges. I had a question related to 2 questions ago on benchmarking essentially different libraries. One thing that I've noticed is that for a lot of the applications of deep learning or machine learning in biology, a lot of the tuning of different models is somewhat arbitrary. And I think it's because there's maybe a lack of tools and methodologies to really do a good comparison of these different frameworks and these different models. So since Amazon is providing this big ecosystem of different libraries for people to use, have you guys given any thought to any sort of tooling to allow people to understand the performance increases or maybe even usability or other different comparisons for different libraries or on different infrastructures?
Yeah, that's something we've left up to the community to decide. So if you look at the ICGC TCGA DREAM Challenge that you guys are running on RNA-seq data is a perfect example. I think that the DREAM organization is really, and Precision FDA, other things that are out there that are looking at defining what is truth and how to assess that truth is the way to go. Honestly, we're focused on infrastructure and services and kind of business problems. For us to dictate what is gold is A, inappropriate, and you guys are better at it. So we'd love to work and promote that sort of benchmarking work, so please reach out to me. My email is here. If you have a project or a problem or have ideas of how to work with the data to create those validation frameworks, right? We don't want to say this is truth and this is standard. We want to say, how do you assess something as quality with respect to what else is out there? So that's something we work with. We work with the Global Alliance. We obviously work with the NCI a lot. Please reach out and we'll make sure that we're involved in that process. But to say what is truth and what is better, that's not our business. Great.
Got one final question here in the room.
Thanks. What's your opinion on quantum machine learning and its potential?
I'll believe it when I see it, I guess. It's really, it has a lot of promise, but, not much I can say about it. Let's put it that way.
Great. We're out of time, so I got one quick announcement. First of all, the speaker series is going on hiatus for the rest of the summer. So watch your emails for a new list coming out of speakers being scheduled for the fall. And with that, let's thank Angel for a terrific presentation and conversation.